Thank you very much. So it's a pleasure to give you a very high-level overview of the solar wind interaction with Pluto's atmosphere. But I wanted to start with this fabulous picture of Pluto, my favorite picture of all time, but also shows the atmosphere so clearly with the haze layers there. And it's this solar wind interaction with that atmosphere that I'm going to focus on today. So let's start with some SWAP data that Ralph mentioned. This is the low energy solar wind, as in the name of the instrument, solar wind measurements. At the top layer, you see the total fluxes wiggling about in intensity, fluxes of the solar wind particles, but also the second line, you'll see the blue is the solar wind and the red are the heavy ions. And we believe these to be methane plus ions coming from Pluto and being ionized. You see that the spacecraft entered on the flank of this interaction region and then exited about 101 Pluto radii down tail. And we measured a net flux of material going down the tail of about 5 × 10⁻23 particles per second. This is methane plus ions flowing at about 100 meters per second. So much slower than solar wind, slow flux down the tail. Now, if we zoom in, the crossing of these boundaries, which is shown to be very sharp in this sort of like textbook picture, was in fact much more fuzzy, these boundaries. But we concluded that if you take where we crossed from the solar wind into the Plutosphere, that the Pluto pores is about 2.5 Pluto radii, and the upstream bow shock, where the solar wind goes from supersonic to subsonic, is about 4.5 Pluto radii. Now, these fuzzy boundaries are fuzzy because the weak magnetic field, but also, and the solar wind being very variable out there, the outer solar system, but also because there are upstream of this interaction, there are some ions that are produced from the ionization of the escaping atmosphere, these pickup ions, where you have a large gyre radius because the magnetic field is weak, and so those newly produced ions have a very large gyre radius, and so you see them going vertically up out of the system. Now, if we then look at the Pepsi results, which Ralph talked about, indeed published by Peter Coleman, these show different populations, here shown with different colors, different directions, different energies. But the notable point is that in the wake, there seem to be some oscillating fluxes. And what the cartoon that Peter inferred from this is that directly behind Pluto, there's a sort of emptying of or deflection of energetic particles around the interaction region. And then these particles get deflected into and fill up the wake behind, refilling the region behind. And this is sort of become the cartoon of what we think is this interaction of the background interstellar pickup ions, superthermal ions that Ralph was talking about, interacting with this region, with the atmosphere, and the plasma perturbations that are really caused at lower energies by the deflection of the solar wind and the ionization material near Pluto. Now, since the flyby, there have been models which have helped us understand what's really going on, what the structure's like, and how this process works. These are models that treat the system as a combination of a fluid, which is the sort of electrons in the magnetic field, but the particles, because of the large gyre radius, have to be treated as separate particles. So these hybrid models, such as this one by Faye Arbent, shows that there is this the weak field around produces the large gyre radius of pickup ions, And he inferred that there was a magnetic field in the background of about 0.3 nanotesla. And that was a sort of at the upper range of the predictions that we made based on Voyager observations of the magnetic field for this region. But again, the effects of the pickup ions was to produce this asymmetric interaction. Further modeling, similar hybrid code produced by Nathan Barnes inferred a somewhat weaker field for about 0.1 nanotesla. Again, very kinetic interaction with this system vibrating and juddering, if you like, as the solar wind goes past and interacts with the atmosphere, the ionized layers of the atmosphere. So then there's been modeling more recently here of the Pepsi interaction consistent with the schematic that Peter Coleman produced, showing this depletion in the wake of the energetic particles and then asymmetric tail downstream. There's another model that has happened that has more recently, sorry, not so recently, the Hale and Patey one from the 2017. They looked at this interaction and thought about what would be the role of Charon in this. And they showed, depending on where Charon is in its orbit, if it's downstream, doesn't really make much difference. But if it's upstream, it deflects some of the flow around Pluto. And so the interaction region is, if you like, Pluto's region is sheltered by this interaction a little bit with Charon. Now, the last slide I want to show, well, first of all, a list of my conclusions, that this is a small, weak, comet-like interaction of the solar wind with the escaping atmosphere, which becomes ionized, so methane escape flux. What we see is about 1% of the atmospheric escape, neutral atmosphere, becomes ionized, photoionized, or charge exchange, but mostly photoionized to produce 5 × 10⁻23 ions per second escaping. And then the pickup of those ions produces this large-scale asymmetric interaction region. Energetic particles are depleted in the wake, and that Charon perturbs the system. Now, what would be interesting would be to think about, given what we've learnt at Pluto with an atmosphere at the time that we were observing, what happens with the seasonal variation? What happens when the atmosphere maybe gets weaker, further away from the sun? Maybe there's more particles hitting the surface. There's the radiolysis. What about other objects in the Kuiper belt that maybe have less of an atmosphere, smaller? What about the radiolysis of their ices on the surface? This could be important for the chemistry of what's going on of the ice and volatile systems. I think there's a lot more work to be done on this to think about what the implications are of these charged particles in the outer solar system impacting these icy bodies. I'll end with a really interesting sort of recent results. Dave Brain's group at the University of Colorado in Boulder, they looked at this some years back and thought about, well, what happens if we look at different atmospheres throughout the solar system, the solar wind interaction with these atmospheres? These are planets that don't have magnetic fields and have interaction of the solar wind with their atmosphere. And what he found was that even though these objects are very different in size, the actual interaction of the solar wind or the surrounding magnetospheric plasma with these objects produces a similar size interaction region, similar in scale, even though this is across the entire solar system, and a similar loss rate of a few kilograms per second. And this seemed bizarre. Now, the exception to that, of course, is the comets, which come in and actually dump as much as tons a second. But if we just look at the planets, objects with atmospheres interacting with the solar wind or with the magnetosphere, you end up with a similar number. And his group is now coming up with theories for explaining this, and Parker Hinton has a new paper that sort of describes how, if you look at the interaction of the plasma with the atmosphere, you end up limiting it, either because you're limiting the amount of ionization or you're limiting the amount of stuff coming out. This is an interesting theory that's coming out of these, looking at these interactions. And with that, I will end. Thank you very much.
Any questions?
Is he asking a question or is he going to the restroom? Who's asking a question? Excellent.
Fran, I have a question, but it's so simple, I'm almost afraid to ask it.
That's
When you've got loss rates of a few kilograms for Pluto compared to tons for a comet, does that mean that if we had good enough imaging, we could see an ion tail and a dust tail coming off of Pluto?
Oh, that's a good question. No, I don't think so. In that we're not seeing see what you're seeing with the comet when it's dumping tons in is when it's close to the sun and it's heating up everything and you're just breaking it apart, right? Whereas what we're seeing out in the Kuiper Belt is just an interaction around the atmosphere. So it's a boundary layer effect, right? You have a little bit of upstream pickup ions, you have a little bit of deflection and so on. You're not hitting the surface or heating the surface and making dust come flying off. Yes, there's a little bit of impacts on the surface by meteorite equivalents that are out there that maybe produce some dust. But I don't think that there's anything like a dust tail. And Mihai, if there's any evidence in the student dust detector of a tail, please let me know. But I don't think we detected one.
I think instead of a tail, you will have a torus. The escape speed is comparable to the orbital speed, or even less. So instead of making a large tail by radiation pressure or plasma drag, you make a torus.
Right.
Good morning, Kerry Liss, APL. So Fran, as you know, there's a lot of information we can help you with the charge exchange interaction between the solar wind and these atmospheres we see in the X-ray. Fran's been my co-eye on many of our observations, including the putative detection of X-rays from Pluto. To help answer your question, what we've learned from looking at comets in the X-ray versus the planets is the planets have a neutral gas envelope which interacts with the solar wind, but it's only a few times the radius of the planet. It's very small. So it's on the order of thousands of kilometers. A comet has a coma that's typically 10 to the 5, 10 to the 6 kilometers. It's huge. It's 100,000 and million. So it can scoop up and interact with a lot more solar wind, and you get a lot more charge exchange interaction. So it's a volume effect, it's a scale effect, just like you heard Mihai and Fran suggesting. But we know that for a fact. If you had infinite precision, could you actually see structures around Pluto? Probably yes. So what we need is more X-rays, actually, in my humble opinion, instead of staring at these objects more. We've asked for XMM time to go back to look at Pluto again during the solar max, see if we can learn more about the system.
Or we could take Pluto and bring it into the inner solar system and see what happened to it.
And you touched upon it. It's true that Pluto's escape rate is roughly the same as a 1 kilometer comet at about 1 AU. Even though it's much, much bigger object, the total amount of mass of material is about the same. So they are acting somewhat similarly, but on very different length scales.
Cool.
We can talk offline, Elliot.
Maybe I have a quick question about your next slide about comparative planetology. Why for Titan the color is different? Why for Titan it's pink and not
Titan? So because Titan spends most of its time inside the magnetosphere of Saturn, not out in the solar wind, but you get a similar sort of interaction. You don't actually have so much of a bow shock, but you have a boundary of pause between the outside magnetosphere and the atmosphere interaction. Yeah. But it does go sometimes out into the solar wind, and then you get an upstream bow shock and you get a similar interaction.